Friends, very good morning to everyone. We were discussing with electrophilic substitution reaction in monosubstituted benzenes. We know that when an electron withdrawing group is there, it withdraws the electrons from the ring system and make the system electron deficient. Once it becomes electron deficient, it becomes deactivated. It is something like we have money with us and that money is taken away from someone, then we get deactivated. Then our reactivity reduces. Same is the case here that it decreases the rate of the reaction. Today's subject of discussion is the effect of another electron withdrawing group, the halogens. When the halogens are there as a substituent on benzene ring system, it withdraws the electrons as it is electron withdrawing and make the system electron deficient and deactivate it and again decreases the reaction. When there is an electron withdrawing group, it should decrease the rate of reaction and it is always meta directing. However, these halogens, though they are deactivating, though they decrease the rate of the reaction, they give orthopara directing compounds. Why is it? How is it? Is the subject of discussion for today's class. To know that, let us look into the mechanism of reaction. When we take halobenzene, the chlorobenzene as an example, the pi electrons can move towards the ortho position and the electrons become concentrated on the carbon at the ortho position and it gives rise to electron rich center, a carbene ion. This attacks on the nitronium ion and the ortho attack takes place. When the ortho attack takes place, the carbon and nitrogen bond is formed between the nitronium ion and the carbon at the ortho position. As the electrons are moved over the ortho position carbon, the adjacent carbon become positive center. To satisfy this positive center, the pi electrons from the adjacent carbon moves. Once it moves, the positive center over here is satisfied and the carbon from which it has moved, that becomes electron deficient, that is a new carbocation is formed. To satisfy this positive center, the pi electrons from the adjacent carbon moves, creating another positive center at the meta position. The carbon-hydrogen bond breaks and those electrons are utilized to satisfy this positive center and gives rise to orthonitrochlorobenzene with the removal of H+. Thus, the electrophilic substitution occurs. Similar fashion, there are lone pair of electrons on the chlorine. These electrons can also give to the positive center and it can satisfy the positive center and it gives rise to the fourth canonical form 1D. When ortho attack takes place, there are four canonical forms found 1A, 1B, 1C and 1D. Let us look at the attack at the meta position. The pi electrons can move over here, creating a carbene ion at the meta position. This electron-rich center attack on the nitronium ion and the meta attack takes place, creating a positive center at the para position. To satisfy this positive center, the pi electrons from the adjacent carbon moves to give rise to a positive center at the ortho position. To satisfy this new positive center which is formed, the pi electrons from the adjacent carbon moves and it gets satisfied, creating a new positive center. This is something like I have problem and my neighbor helps me. When my neighbor helps me, he will be under problem. Something like this. The carbon hydrogen bond breaks and those electrons are utilized to satisfy the positive center and H plus gets removed away and I get meta-nitrochlorobenzene. Let us look when it attacks at the para position. The pi electrons can move towards the para position and a carbon ion is formed. This attacks on the nitronium ion and gives a substitution at para position by nitronium ion and creating a positive center at the meta position. To satisfy this positive center, the pi electrons moves to the next position and gives rise to a positive center on the carbon to which an electron withdrawing group, that is chlorine, is attached. The new positive center is satisfied by the movement of the pi electrons from the adjacent carbon in this fashion and gives rise to a positive center at the meta position. The carbon hydrogen bond breaks. The electrons of this carbon hydrogen bond are utilized to satisfy this positive center and it gives rise to para nitrochlorobenzene. Here you see in case of 3b, the positive center is formed at the position where there is chlorine is attached to it. The lone pair of electrons on the chlorine can also move and satisfy this positive center along with this and gives rise to a new canonical form 3D. If you see this ortho attack, para attack and meta attack, when ortho attack takes place and para attack takes place, four canonical forms are formed, and when meta attack takes place, three canonical forms are formed. Right? As the more canonical forms are formed, more is the stability of the intermediates in the ortho attack and the para attack. Thus, when there is an halogen group, ortho-para attack is the preferable site of attack and it always gives the ortho-para directing group. Overall, the deactivating groups, that is electron withdrawing groups, are generally meta-directing and this comes under the category of strongly deactivating and moderately deactivating groups. The strongly deactivating groups includes nitronium ion, ammonium ion, trifluoromethyl ion and trichloromethane ion. The moderately deactivating group includes aldehyde, ketonic, carboxylic, esters, amides, sulfonic acids and nitrates. This is the second category which we have. They are ring deactivating and ortho-para directing. Those are halogens. Halogens come under the category of weakly deactivating group. Fluorine, chlorine, bromine and iodine. When there is halogens, it is ring deactivating and thus it decreases the rate of the reaction. But still it is ortho-para directing. Whereas other groups which come under moderately deactivating and strongly deactivating structures, it will be always meta-directing. Thank you. The next topic we will be dealing with the effect of electron donating group on the reactivity and orientation of monosubstituted benzenes.